Now we'll just go through your transmission gate. Transmission gate means normally it is known as your TG. Okay, so this one is the symbolic diagram of a transmission gate where your PFET as well as NFET is being placed. Okay, so it is being controlled by the site S bar as well as S, or sometimes it is represented as an S bar. So it is left to you depending upon your design. So whatever the input will be, the same will be the output when S is equal to 1. So if S is equal to 1 means your NFET will be on. So obviously at that time S bar is equal to 0. So PFET will be on. So both the transistors will be in a on state. So whatever the input will be, that they will be getting at the output. So there will be no threshold voltage drop. Okay, so this one is your symbolic diagram. So this one is your schematic of your transmission gate where PFET is connected and NFET will be connected. So if I just consider this as a truth table, when S is equal to 0 means, for this S is equal to 0 means S bar will be 1. Okay, so what it will happen, so the S bar is 1 means your PFET will be in off state as well as your NFET will be in a off state. So there will be no connection between the input as well as the output. So it might be having the previous value. Okay, when S is equal to 1 and S bar is equal to 0, both the FETs will be in a on state, that is PFET as well as the NFET. So whatever the input will be, the same will be getting at the output, that is output is equal to input. Okay, without any threshold voltage drop loss. Okay, next. So now this one is your simple XOR gate using your transmission gate. Okay, just for your reference. So this can be drawn in a other fashion, that will be just coming it later. So the expression for your XOR gate is what? Y is equal to A bar B plus AB bar A excludes your bar. Okay, so this one is the schematic representation of your XOR gate using your transmission gate. Okay, so two transmission gate we require. Okay, now so when B is equal to 0, okay, when B is equal to 0, the first transmission gate is on, that is TG0 is on state. Okay, at that time TG1 will be in a off state. When B is equal to 1, the TG0 will be in a off state and TG1 will be in a on state. Okay, so that will get just comparing how the what are the connection you have made it right or wrong by using comparing with your truth table. So when both the inputs A and B are 0 0, what will happen? So what is the output? Okay, when A is equal to 0, B is equal to 0, the transmission gate is will be getting at the output as 0, because this TG0 will be in a on state. So whatever the value will be, that will be getting it as a, when A is equal to 0 means obviously AY is equal to 0. Okay, next, when A is equal to 0 and B is equal to 1. So B is equal to 1 means this transmission gate is in a off state. So this TG1 will be in a on state. Okay, so 0 A is 0 here, so you just connected with the A bar means I will be getting the output as input as 1 here, so the output will be what? 1. So when 0 1, output is 1. So in the same fashion for 1 0, it is transmission J0 is 0 is on, TG1 is off. So what I'll be getting is, since A is equal to 1, that I will be getting it as the output. Okay, when 1 1, so obviously your TG1 will be in a on state. So A is 1 means, so here we will be getting it as a 0. So obviously Y is equal to 0. Okay, so this, the logical diagram whatever you have drawn is correct according to this truth table. Okay, so this one is for XOR gate. If I want to do for the same thing for XNOR gate, what I should be doing, only one thing what I will be changing is I will be representing the B. The remaining structure will be same. I will just change to B to B bar and B bar to B. So then the conversion will be of a XNOR gate. Okay, this will be just cross checking in the later. So okay, now we'll just be going through your full adder using transmission gate. Okay, full adder using your transmission gate. Okay. Okay, so this is the simple form of writing the truth table as usual, a common way, that is it is having 3 inputs ABC in and 2 other outputs sum and Cout. Okay. Next, the simple form of this table, how it can be written as, so you just take the 2 outputs sum and Cout. Okay, and they will just take the expression it as A excludes your B. Okay, just to represent how it is been. Okay, see here in sum. Okay, the sum is 0 1, Cin also is 0 1, so to write it is in a sum Cin. Okay, in the C out, okay, so 0 0 is there, so B is also 0 0, A is also 0 0. Just for our confirmation or easier way, we'll write it as A. Okay, now A excludes your B, that is A B. The 0 0 means the output is 0. Okay, next in this fashion. Next sum, in the second bit 1 0, sum is 1 0, but Cin is what here? 0 1, so it is a complementary form. So when it is 0 it is 1, when it is 1 it is 0. So we'll write it as Cin bar. Okay, what is the C out now? 0 1, so here also it is 0 1, so we'll write it as Cin. Okay, next the A exclusive for 0 1 is what? 1. Okay, next in the same fashion for 1 0, what it will be having? So sum is what? 1 0, for C is also 0 1, so it is also the complementary form. Okay, what is about the C out? It is 0 1, so C in also is 0 1, so write it as C in. Okay, and the next when it is 1 0, the exclusive gate is what here? 1. Okay, next for 1 1, then that sum is 0 1, C in also is 0 1, so write it as C in as C in. For in a sum it is writing as C in. Okay, for C out it is 1 1, so here also it is 1 1, so write it as A. Okay, next for 1 1 exclusive gate it is 0. Okay, now see here. Next, the two first row as well as the last row, C in is there, A is there, and 0. So here also it is C in and 0. Okay, so instead of writing two rows, you write it as only one, that is C in A as 0. Okay, next second and third, so it is C in bar, C in and 1. So in this fashion, we write only, we will consider only about what? Two things, that is C in A 0, C in bar, C in 1. Okay, next. For the expression for how we will be writing it as for sum. For sum it is what here? C in. For sum it is C in. It is 0. So what I will write it as? A excludes your B whole bar. Okay. For C sum it is what here? C in. Okay. Next is what here? 0. So what it is 0 means? It's a complement form. A excludes your B whole bar. Plus. Okay. C in bar. And it is 1. So we are already writing it as A excludes your B. C in into A excludes your bar whole bar plus C in bar into A excludes your B. Okay. Instead of A excludes your bar, in short form we want it, can write it as P. So the expression what we will be writing here is C in into P bar plus C in bar into P. In the same fashion, for C out what it will be writing is C out is C in into, sorry, C out is what? A into A excludes your B whole bar, since it is 0. So what it will be? A into P bar plus C in into P. Okay, for C out it is A into P bar plus C in into P. Okay, so this is the reduced expression of this truth table what we have been formed. Okay, next. So this is the XOR implementation using transmission gate. Previously also we have done by using the two transmission gates. Okay, so here we have taken here one transmission gate along with one PFET as well as NFET connected in this fashion. Okay, so B is there, A is being connected to PFET and the A bar is being connected toward the N. Okay, B. Okay, so P is the thing what will be just consider P1 and N1. So this is the structure. If you just give the input A is equal to 0 and B is equal to 0. If A is equal to 0, this transmission gate is on. So what the output will be getting here is B value is 0. So we are getting it as 0. Okay, when A is equal to 0, here is what? So 0 1. So B is 1. So we are getting it as 1. Okay, next. When A is equal to 1, so this transmission gate is in a off state. Okay, this transmission gate is in a off state. So what will happen here? Okay, next, when A is equal to 1, this transmission gate is in a off state. Okay, so B is what here? 0. So see here, this structure looks like as it is connected in a inverted form. Okay, so when B is 0, the output will be at the P is what here? We'll be getting it as 1. Okay, when A is equal to 1 and B is equal to 1. So here at this form A is equal to 1 means this transmission gate will be in a off state. So when B is equal to 1 means it's converted into 0. So this also obeys the truth table of your XOR gate. The implementation whatever is done is correct. Okay, So these are the 4 cases what it will be, as we mentioned. So the A is equal to 0, transmission gate is on while P and N is off, like this. So these are the 4 transistors operation. So 4 cases. Okay, for your reference you can just go through it. Okay, next. So this one is the simplified form of representing your full adder using the transmission gate. Okay, see here. So these two are been just represented. So some is we have taken it, and see how the expression what previously what we are just the same thing. Okay, so here what we are connected is the above part. It is same as your the XOR gate connection previously. Just before that you just cross check. So this is the connection what you have done. Okay, so the same form it is been copied and it is been placed and the connection has been done. Okay, the first part, that is above the line, that if I just take, so this part is known as your XOR gate. Okay, and the below one it is representing as your XNOR gate. Okay, why? Because here the connections have been changed here, A and A bar to A bar and A. Okay, as it is been mentioned previously. Okay, so this above part is acting as your XOR gate and the below part is acting as your XNOR gate. Okay, see, so the output here what will be getting is P, and here the output I will be getting is P bar. Okay, see, next. So this is the simplified form of representing the term in a full adder. Okay, Cin into P bar, Cin bar into P. So this is the sum expression what I will be getting, and this is the C out, that is Cin into P bar, the sum expression what will be writing, that is plus Cin bar it plus P. Okay, next for C out it is A into P bar plus Cin into P. Okay, so this is the structure of your full adder. Okay, you can just check here. Sum is equal to what? P excludes your Cin. Okay, Cin bar plus Cin bar into P. Okay, for C out it is A into P bar plus Cin into P. Okay, so this is the schematic of your full adder. Okay, now we'll just discuss about your multiplexer, that is your data selectors. Okay, so it is also represented as a 4-way MUX. So already you know that the formula for is 2 raised to n is to 1. So where 2 raised to n is your inputs, n is your select lines. Okay, so it will be having 2 select lines, so S1 and S0. Just for our representation, S1 bar, S0 and S0 bar, and only the one output. So 4 inputs, 1 output and 2 select lines. Okay, when the select lines S0, S0, 0, 0, we will be getting it as I0. Okay, for 0, 1 it is I1, for 1, 0 it is I2, and for 1, 1 it is I3. Okay, so if I just represent the expression for this one, so just I will be getting it is what? Z is equal to I0 S1 bar S0 bar plus I1 S1 bar S0 plus I2 S1 S0 bar plus I3 S1 and S0. Okay, so this one is just for your NMOS schematic. Okay, so 4 lines representing your I0, I1, I2 and I3. Okay, row wise, and column wise you were taking it as a select lines. Okay, S0, S1 bar, S0, and so these are the connecting. For I0, what are the connecting here? S1 bar and S1 bar. So S1 bar and S0 bar. So you are just connecting the output. Okay, for I1 what it is? S1 bar, S1. So I1 bar is S1 bar S0. Okay, next for I2 it is S1 S0 bar. In the same fashion for I3 it is S1 S0. Okay, so this is the NMOS schematic. Okay, next. So this one just representing a first stick diagram. So I not represented by using your n, since it is a just drawing for the NMOS, so you can consider it as a n plus diffusion, and the select lines are being connected by using the metal lines. Okay, and the connectors are being used by using your polysilicon, that is your gate region. Okay, the same representation by using the thing. Okay, see for I naught it is what? S1 bar S0 bar. So these are the connected. The gate is being connected by using from metal to wires yours n plus diffusion. Okay, so the dotted lines are being representing your gate region. The dark lines are be representing a metal, and I naught are represented with your N plus diffusion. Okay, so this one is the standard cell representation of your 4:1 mux. So the length and width have been mentioned. Okay, 7 lambda across 4 lambda. So this is the connectors what you'll be using. Okay, so this one is for stick diagram. So this one is for your layout. Okay, so this is the structure, the same thing. Okay, what you are represented in schema. So this one is your N switched based multiplexer. So this one is known as your 4-way multiplexer. S1 S1 bar, S0 bar, I0 I1. Okay, for I0 it is S1 bar N. So these are the connectors what you have been just connected. Okay, and see 7 lambda. So total it is what it is having is 20. So 4 connectors lines are being used for the metals. So it is 7 cross 4 means 28 lambda, and okay, 11 lambda is the one connector. So it is of a 4 rows of a N plus diffusion. So we are taking it as 44 lambda. So the total length is of 28 lambda cross 44 lambda. Okay, so this one is your 4-way NMOS switch. Okay, so these are just the connect. Okay, so this is the general logic function of your 4:1 mux. Okay, so here just represented the A bar A, B bar and B bar, and the selectants are so the inputs are be represented as C3, C2, C1 and C0. Okay, so these are the stuff represented, and Z is equal to, they are just represented the A and B. Okay, so now we'll what consider is A bar A, B bar B will consider it as the select lines S0 bar, S0, S1 bar and S1. Okay, next, and these are the C3, C2, C1 and C0 are represented by your data input, that is I1, I0, I2 and I3. Okay, so this one is the truth table for your thing. Okay, before that, so if I want to represent the formula for the mux, that is Z is equal to what it is, I0, S1 bar, S0 bar, previously what you have just cross checked, I1 is equal to I1 into S1 bar S0, I2 S1 bar S0. So represented the terms with these terms. Okay, the terms the outside what we have been represented, that is I0 is been represented by C0, S0 bar is S1 bar is represented by B bar, and S0 is represented by A bar. Okay, in this fashion, so the expression is there. So this is the truth table. Okay, so 4 inputs are there. So what is the function what will be just looking like? So when all the inputs are 0, if I just represent the value C0 is 0, whatever might be the things, so all they will be C0, C1, C2, C3, all if I represent, then it is 0. So obviously Z is my 0. Okay, when 0, 0, 0, 1, when C0 is 1, when C0 is 1, so what I will be getting here is remaining steps C1, C2, C3 are 0. So all the times C0 is 0, B1 bar, B bar and A bar. So what it is be A bar into B bar, or it can also be represented. So in this fashion, if I just go representing the values and try to calculate the formula, so I will be getting it as NOR gate, not B, not A, XOR, NAND and on. So this is the table what will be just getting. Okay, so this is the table what will be just getting. So now I'll just design MUX using transmission gate. Okay, so this is the simple structure of the MUX, that is 2:1 MUX. So it is having 2 inputs D0 and D1, and the select line is S and this is Y. So this is the representation of by using your transmission gate. So you just two transmission gates have been just taken, S, S and S bar. Okay, so if I just represent the truth table, when S is equal to 0, this transmission gate is been working. Okay, so whatever the D0 value will be just getting, it is the output. When S is equal to 1, what will happen? So this will be in off state and this will be in a on state, and D1, whatever the D1 value will be having, that will be just getting. So this is the representation what will happen for 0, 1 as well as then. So when X means you don't care, means it is in a off state whatever the getting. Okay, so this is the thing. Okay, another form of representing the transmission gate. So this one is also the representation of a symbolic representation. So the same thing what it can be represented like this also, because in some of the textbook it has been represented like this. Okay, now next, the simple representation of 4:1 MUX. Okay, already you people know about this truth table. Okay, so this the same 2:1 MUX, we have just taken it into a 3 bits. So already you people know it. Okay, so this collected. So in this fashion it will be just represented. This is the stuff. So 2, inputs, one select line, so two outputs are getting. So this is the output. Okay, so S0, S1, I0, I1, I2, I2. So these are my 2:1 mux. So this is also 2:1 mux. So this is also 2:1 mux. The overall structure looks like what? The 4:1 mux. It has been designed by using your 2:1 mux. So in this fashion, it has been just considered and the connections have been made. Yes, not. And if you just go on working, you will be getting the thing. It has the output as 5. So four inputs: I0, I1, I2, I3. Two select lines, S0 and S1, and O is the output. So this is the simple design of 4:1 mux using 2:1 mux. So this is the connection of your transmission gate of